All right, so today's the last class on like mathematical stuff, hand stuff, and then after this we're going to go on to the computer. Last time I brought up the equilibrium equations. So remember the equilibrium equations. Well, let's see, I gave them two different ways. I gave them in terms of stress, and then I gave them in terms of displacement. Anyone remember what the benefit of doing them in terms of displacement is over stress? The problem is that stress has 6 elements, and you only have 3 equations, so you need this other stuff to combine with it in order to come up with answers. It's just that, so those, like basically, I mean, think of it as like if you had 3 variables and 2 equations, okay? You can figure out some relationships between things, but you can't solve. You know, you need more information to solve. You just don't have enough equations. And that's the same thing with doing the equilibrium equations in terms of stress. If you do it in terms of displacement, you have enough information to solve. It just turns out the equations are too hard to really be very useful. In some cases, they can be useful, but... what kind of equations are they? So it's a system of... What kind of equations? Yep, partial, yep. System of partial differential equations. 3 partial differential equations. And normally, if you have them expressed in terms of displacement, you have 3 independent variables. What are those? Yep, x, y, and z. And 3 dependent variables, and those are the displacement components. So that's the vector u. And with any differential equation, you know, you need to solve the equation, and you have to do it subject to boundary conditions, right? The boundary conditions for these come from the loading at the boundaries. So I'm going to do an example to show how that works. Okay, so this example, let's say that you have a big 1 meter by 1 meter by 1 meter cube of steel. Big, huge thing of steel. It's big. And say that you apply a shear traction along the top, like this, that deforms the cube into this parallelogram, like I have drawn here. And let's say that this distributed load is 500,000 pascals. And we'll use this coordinate system. The bottom is fixed. And we're going to ignore gravity on this. The effect of gravity is so small compared to that big distributed load that it wouldn't matter either way. So we want to do 2 things. Let's say that first we want to find the displacement vector as a function of x and y. And actually, this is the coordinate system orientation we're going to use, but let's put it down at the bottom. So let's put the coordinate system down here at this corner. And we're going to do this just based on kind of thinking about what type of deformation we're going to have and using, the ideas of deform. And then the second thing we want to do is figure out, make sure that it satisfies the equilibrium equations. Does it satisfy the equilibrium equations and the boundary conditions? All right, well, this is in a state of pure shear. And so we're going to have the same stress everywhere. If you just think of this thing as like a blown up version of your stress cube, we're going to have constant stress everywhere. And so the stress is going to be, what I have drawn here is giving the yx stress, right? So we know that's the same as the xy stress. There are no tensions or compressions. I didn't give the dimensions, but 1 meter by 1 meter by 1 meter. And so the stress tensor for this is 0, 500,000, 0, 500,000, 0, 0, 0, 0, 0. So it's kind of like the way this problem's defined, what's really given is that stress tensor, okay? But we want to go from this stress tensor to figuring out what the displacement vector is at every point. Well, we know that elasticity lets us go from the stress tensor to the strain, to the Voigt strain. And we know that we have equations that go from the strain to the displacement. So that sort of suggests a reasonable set of steps to get to displacement, right? We're going to first figure out the strain, and then we're going to go from the strain to the displacement. Okay, so did I say steel? Okay. So Young's modulus for steel is 200 times 10 to the 9 pascals. Poisson's ratio for steel, let's use 0.33. So if we write this stress in Voigt notation, it's 0, 0, 0, 0, 0, 500,000. And that's equal to the stiffness matrix. Well, actually, this is, sorry, write this the other way. So we're trying to figure out what the strains are. So the Voigt strain is EXX, EYY, EZZ, EYZ, 2EYZ actually, 2EXZ, and 2EXY. And that's equal to the compliance matrix for steel times the stress tensor, which we know is 0, 0, 0, 0, 0, 500,000. For isotropic materials, the way this matrix works, the stiffness and the compliance matrix both, if you're only dealing with shears, you just have the shear strain is equal to some constant times the shear stress, because you only have that one non-zero component for that row. And so this ends up telling us that 2 EXY is equal to 2 times 1.3. This is just all coming from the form of the compliance matrix, divided by 200 times 10 to the 9th times 500,000. And you get a value of 6.5 times 10 to the minus 6. And so EXY is equal to 3.25 times 10 to the minus 6. What are the units on strain? Yeah, unitless. So this is the complete answer. The 1.3, that just comes if you look at the form of the compliance matrix from a couple days ago. Actually, here's where I got it. And it would be 1.3 if Poisson's ratio was 0.3. Because it's 1 plus Poisson's ratio. So why don't you go up here and let's just use 0.3 for this. It looks like that's what I did through my calculations. Okay, so the next step is we can go from the strain to the displacement. We know that this strain is equal to 1/2 times the partial of ux with respect to y plus the partial of uy with respect to x. And now in order to use this, we're going to have to think a little bit about what we expect from this displacement. So let's go back up. I'm going to go back to the original drawing, and I'm going to draw in what this block looked like before this deformation happened. Okay. And let's think about what the displacement vectors look like at each point. Okay. Down along the bottom row, every starting point that's in that green cube stays in exactly the same spot, right? It's fixed to the ground, so there's no displacement there. Up at the top, each one of these points translates this way, right? There's a displacement in the x direction. Okay. So up at the top, there's an x displacement, but no y displacement, no z displacement. If you go halfway down, you get the same story, but just not as big. And so if you think about it that way, here's what we know we can expect from the displacements. We expect the displacements to be 0 in the y and z direction. And in the x direction, we expect them to be linear with the y component, right? It's going to be 0 when y is equal to 0 and biggest when y is at its highest, okay? So we expect ux to be equal to some constant cx times y, uy to be equal to 0, and uz to be equal to 0. And now we just have to figure out what that cx is. Mm-hmm.
If you go back to the previous slide,
Yeah.
There's a x displacement, but isn't there also a y displacement because the bar is kind of tilted so that if you look at like,
In pure shear like this, I think the answer is no. But it's possible that I'm thinking of a small deformation. If it's a small deformation, like smaller than I have it drawn, like I have it exaggerated, you know. But if it's small, then those changes in angle are going to be a lot more noticeable than changes in height. So to be on the safe side, let's think about it that way. But I think actually, if with a shearing load like that, that height would stay the same. Yeah. Okay, so now we have this form, and we can plug this into this relationship, okay? So we can use this form of the displacement up in this equation. So we have 3.25 times 10 to the minus 6 is equal to 1/2 of d dy of the x component of the displacement. So the x component of the displacement is cxy. And then plus the partial with respect to x of the y component of the displacement. What's the y component of the displacement? 0, yep. So that's going to go away. And we end up with this equation that says 3.25 times 10 to the minus 6 is equal to cx over 2. And so then just solve for cx. Cx is equal to 6.5 times 10 to the minus 6. And so the final answer is our displacement vector is equal to 6.5 times 10 to the minus 6 times y, 0, 0. Any other questions about that? So that's the sort of deform part. And now we just have to use this in the equations, the equilibrium equations, to check and make sure that it holds. Like I said last time, it's a lot easier to check that something satisfies those equations than it is to find an answer out of the blue. All we have to do is take those partial derivatives and make sure that the equation holds. All right, so remember those equilibrium equations. So we're going to plug these into the equilibrium equations. Make sure they're satisfied. The equilibrium equations were, I'm just going to write one of these three, and I think you'll see what's going on here with the equations. The first one says this constant k1 times the partial of ux with respect to x, the second partial of ux with respect to x, plus k3 times the second partial of ux with respect to y, plus K3 times the second partial of ux with respect to z plus K4 times the second partial of uy dy dx plus K4 times the second partial of uz dz dx plus that body force. That would be gravity, but we're ignoring gravity for this problem, so that's 0. Has to be equal to 0. Okay, and then we have the second and third. But basically, we want to plug our expression for the displacement into this equation and make sure that it holds. Well, you can see it's going to hold because all of these are second partial derivatives, right? This is the only non-zero term here is linear in y. And so ux with respect to x is 0, with respect to z is 0. These are 0, right? Look at this one here. The second partial of ux with respect to y. You take your first derivative with respect to y, and this would be a constant. You take your second derivative and it goes away. So this linear function that represents displacement satisfies this equation. Okay. So the equations are satisfied because, you know, it gives 0 equals 0. The only examples that you're going to have to do, like to get ready for the exam, are going to be like this form. You're going to have linear functions, and you're just going to end up with 0 equals 0. Okay, that's not how all solutions are. If you have more complicated things, then it's satisfied for other reasons. But this is the only thing you're going to see. And so now the only thing that we have to make sure about is that the boundary conditions are satisfied. Okay, it's sort of trivial that this satisfies the differential equations, but now we have to make sure that the loads at the edges satisfy, that are satisfied by this displacement. Okay, so how are we going to do that? Well, down at the bottom, the boundary condition says that every point along that bottom has to have a displacement of 0, 0, 0, right? It's fixed to the floor. So does our function for displacement satisfy that? Yep. Y is equal to 0, so you have 0, 0, 0. At the top, our boundary condition says that the traction is equal to positive 500,000 pascals, 0, 0. So now we have, does that make sense where that came from? I mean, that's just the load that I applied at the top on this problem. So how do we check the traction? So we're going to do this as the stress tensor that corresponds to this times its normal. Okay? Remember, traction is equal to the stress tensor times the outward facing normal. The stress tensor that corresponds to this, well, we actually started with the stress tensor and worked our way back to get the displacement. So we already know that the stress tensor is equal to 0, 500,000, 0, 500,000, 0, 0, 0, 0, 0. What's the outward facing normal to the top? Yep, 0, 1, 0. And this gives 500,000 pascals, 0, 0. Any questions about that one? So this one's satisfied. And then the last two that we have to check are the sides. Those have to be traction free. There are no loads applied. I'm just going to do it on one because you'll see how it works for the other one. So let's take the left surface, left face. So the traction has to be equal to 0, 0, 0. The stress tensor is the same everywhere. So we have 0, 500,000, 0, 500,000, 0, 0, 0, 0, 0. What's the outward facing normal to the side? And that's right, negative 1, 0, 0. Is that what you said? Since we're on the left. So negative 1, 0, 0. So that's 0. What's going on here? Negative 500,000, 0. What did I do wrong here? No, it should work on each individual side. All right, well, I guess I better look at that, and I'll send an email about it.
It's supposed to be 0, 0, 0, right?
It should be, yeah. Yeah. Okay, so I'll get back to you on that one. Sorry about that.
So the traction represents the force that's being applied.
The traction is like the force vector or the force per area that's being applied to that face. So yeah, it should be equal to 0 because the only place we're applying a force is to the top. And then, you know, at the bottom, there's that reaction force.
It's not only if it's like normal to the normal to that space. Like if it's
The traction,
well, no, like force. So
right, it should not be. It should be any force acting on it.
oh, okay. Doesn't matter what.
Right, that's right. Maybe I can figure that out after class before I leave here or something. I don't know what went wrong there. But this general approach does work. I don't know, I made some mistake on this one. Yes, for sure, yep. Anybody have any questions about this method? Okay. So that's the differential equation form of equilibrium. There's another form of finding equilibrium. It's actually the way that finite element programs are developed, where instead of solving this differential equation, you minimize the potential energy. So another approach. Equilibrium occurs at the minimum potential energy where potential energy is equal to the strain energy. It's 3 terms. The first one is the strain energy. And to make sense out of strain energy, just think of that as like the potential energy that's stored in a spring when you deform it. You know, the shortening or lengthening of the spring. It's holding that energy. That's its strain energy. Minus the work done by body forces, usually the weight. So let's say work done by weight and other body forces. And then minus the work done by external loads. So if you calculate these 3 things, do this sum, you end up with a number, and that represents a certain deformation. And if you find the minimum of all the possible deformations, that's at the equilibrium. Okay? So this potential energy represents any one single deformation of the body. And the minimum of all those is the one that actually occurs. Okay. So let me first define strain energy. Divide the body up into infinitesimal volume elements. Then the strain energy density for that element, that infinitesimal element, is 1/2 times the Voigt strain, the Voigt stress, dotted with the Voigt strain. And so if that is for one of those elements, then the total strain energy is the integral over the entire volume of the object of 1/2 Voigt stress dotted with Voigt strain dV. By the way, I guess I won't write it here, but just like we did with the differential equations, you can write, because of elasticity, you can write this stress in terms of displacements and this strain in terms of displacements. So you can write the strain energy in terms of nothing but displacements. And numerically, that's sort of the approach that they use in developing finite elements. The work done by body forces by gravity and other body forces if B represents the force per area, this should be a force per volume, for an infinitesimal volume element, the total work done here is the integral over the entire volume of the body force dotted with the displacement at that location, dV. This is the same B that is in those equilibrium equations. And then the last one is the work done by the boundary forces. So represent the external loads as traction T acting on the object's outer surface. Then the total work is the integral, this time over that external surface area, call that A, of the traction dotted with the displacement dA. So all together, to find equilibrium, you want to minimize the integral over the volume of 1/2 times the Voigt stress dotted with the Voigt strain, dV, minus the integral over the volume of the body force dotted with the displacement, dV, minus the integral over the surface area of the traction dotted with U dA. That's the expression for the total potential energy. So now finite elements is a numerical minimization of this It's called a functional. Anyone talked about functionals in classes at all before? Do you remember what that means? So a functional is an integral that, as an argument, takes an entire function. And so if you're trying to find, like if you're trying to find the minimum of a function, you're trying to find the x value, say, that gets you to the lowest point of this function. With a functional, you're trying to find the entire function that minimizes an integral that depends on that function. It comes up in a lot of different kinds of math, and that's what this is called. The basic idea is break the object up into a mesh that has nodes at the vertices of its elements. So like, for example, if this is your shape, you choose a node here, a node here, a node here, a node here. These are the nodes. this is the element. And the mesh is the, combined all of these elements. And you solve the problem by finding all of the displacement vectors at each node, or finding the one displacement vector at each node. One little thing that's worth keeping in mind, so notice, knowing the displacement values, the U values, at the nodes isn't enough to define the functional value. Isn't enough to define the potential energy in this case. And you can see it if you think of it like this. Say that this represents, so say these are your nodes. Okay, so this is node 1, 2, 3, 4, 5. Okay, what's the integral? What's the integral under this curve that's defined by these 5 nodes? Well, it depends on what your interpolating function looks like, right? If your interpolating function is linear, you get one value for that integral, right? If your interpolating function is quadratic, you might get something like this, and then that's a different area underneath that curve. So you also need to choose an interpolating function. The obvious interpolating function would be just lines in between. But you can also get better approximations by using higher ordered polynomials between those. And that sort of gives you the 2 different ways that you can improve the accuracy of a finite element calculation. So there's 2 ways to improve the accuracy of the approximation. The first one is put the nodes closer together. That's making it a finer mesh. And this is the approach that a lot of finite element software packages use, and this is called H-type finite elements, because you can think of H as like the distance in between those 2 nodes. The other way you can improve the accuracy is keep the nodes in the same place, but increase the polynomial interpolating function. That's called p-type for polynomial. And a lot of software packages use the p-type. The one that we're using, Creo, uses this p-type. There's no reason one is better than the other one. They're just sort of two different approaches. That's something to keep in mind when we start doing finite element calculations, that as you're making an effort to try to get your thing to converge by doing more and more accurate calculations, and that's a process that we'll do. The way the Creo software is doing it is keeping the mesh the same and increasing the order of the polynomial in between the two nodes. So Creo uses the p-type. The benefit of that is that remeshing, like coming up with a new workable set of nodes takes a lot of computer time. And so Creo uses this approach where you don't have to keep going through that expensive process of coming up with a new set of nodes that'll work. The downside is doing all these calculations with higher order polynomials is also, computationally expensive. So you gain some and you lose some. Anyone have any questions about that? Okay, there are two problems at the end of the assignment. It's not an assignment, you don't have to turn it in, but those practice problems I gave you, where I gave you problems and you just have to go through the exercise of plugging everything into this potential energy formula and coming up with a total potential energy. So you're not going to minimize it. That'd be pretty much impossible to do by hand, but you're just going to calculate it, so you make sure you sort of ingrain in your head how that all works. Okay, and I think you all, so now you have the practice problems and you have all the solutions to them. I'm going to be gone next week. If you have any questions, you can email me. I'll be on email. But the thing that I want you to do, besides just working through those practice problems and going through the notes and the example problems and getting ready for the exam that's going to be the next week, is in the Creo Parametric book, it starts out with a chapter, I guess they call it Introduction. And it kind of talks about computer-aided design in general, talks a little bit about the layout of Creo. If you've never used any kind of solid modeler before, you might want to skim through that and see if there's anything useful. But I think most of you can just skip that introduction. I don't think you should have any problem. But what I'd like you to do is work through lesson 1 in this book. Okay. You don't have to do it in like tremendous detail. I just want you to sort of follow how to do the kind of objects that they're describing. And we're just slowly going to work our way through understanding Creo and then move into finite elements. Yeah. Oh yeah, well, that's a good question. You need to be comfortable with we'll be doing, not in like full detail, but we'll be eventually doing everything up through lesson 8. Okay, so yeah, I mean, I think anytime you spend just playing around with Creo Parametric, looking through the book, working through things will help you. You know, just little by little, your hands start to know what to do. So yeah, 1 through 8, I would say. I would say don't worry about following every single detail of those, but kind of skim your way through making those parts. Any other questions? Okay. Well, that's it. Thanks.